Welcome to your Algebra 2 video on data creation. Today you're going to understand how and why data sets are produced through observational studies and experiments, and you're going to use the principles of experimental design to create valid experiments. Okay, so when we are producing data, researchers use either observational studies or experiments, and they pick which one they're going to use based on their goal and what they are trying to demonstrate through their study. So whether we're talking one variable or two, it is possible that they're going to use an observational study or an experiment. An experiment is chosen if what the researchers want to be able to show is causation, that one variable causes a change in another variable, and not just correlation, which is basically that there's a pattern that as one variable increases, so does the other, or as one variable decreases, so does the other. A well-designed experiment is the only way we can show causation. In an observational study, researchers don't assign choices. They simply observe them. So they watch what people choose to do, and then they see what kind of outcomes they have. And so there's no manipulation of any of the variables, and there's no random assignment of subjects to treatments. Now, people may be randomly selected, but then the researchers just watch what unfolds. So here's an example. In 1981, a study at Mission Viejo High School in California, researchers compared the scholastic performance of music students with that of non-music students. The music students had an overall GPA of 3.59, and non-music students had an overall GPA of 2.91. Since the researchers did not assign students to get music education and simply observed students in the wild, just let them make whatever decisions they would make and then see what happens, it was an observational study. Since the study observed grades that the students had already made, it was a retrospective study. So it looked backwards. Just like if we have a retro day, that means you're dressing and acting like a time that's gone by. Retroactive studies use data that already exist. If the studies observed grades made by the students after they were selected, okay, so you select the students and then for the next 3 or 4 years you watch their grades. That would have been a prospective study. So prospective studies look forward. All right, so observational studies are valuable for discovering trends and possible relationships. So what that Mission Viejo example did was demonstrate, well, perhaps there is a relationship between music, being involved in music and making better grades. Perhaps being involved in music causes better grades, or perhaps students who are more serious, more academically minded to begin with, choose to be involved in music and tend to make better grades. It could be to have like a no pass, no play system, and so being involved in band or choir or orchestra gives students motivation to participate in their studies as well as in their music program to the point where they're passing and doing well. And so there could be some other factor out there that's actually causing the response. We don't know just based on the observational study. All we know is there's a trend there. There's a possible causal relationship. It is not possible for observational studies to demonstrate a causal relationship. You will hear over and over in these types of courses, correlation does not imply causation. If you want to establish causation, you have to conduct a well-designed experiment. An experiment is a study design that allows us to prove a cause and effect relationship. And the way this is done is through the characteristics of the experiment. An experiment manipulates factor levels to create treatments. Okay, we come up with different values for a variable that we think is going to cause different responses. And then here is the critical characteristic of an experiment. An experiment randomly assigns subjects to treatments. In an experiment, you never let the subjects choose which treatment they will receive. At the end, an experiment compares the responses of the subject groups across treatments. In an experiment, the experimenter must identify at least one explanatory variable, called a factor, to manipulate, and at least one response variable to measure. So whatever you think is going to cause the change is the explanatory variable. Whatever you think is going to be changed is the response variable. In an experiment, the experimenter actively and deliberately manipulates the factors to control the details of the possible treatments and assigns the subjects to those treatments at random. The experimenter then observes the response variable and compares responses for different groups of subjects who have been treated differently. In general, the individuals on whom or which we experiment are called experimental units. Okay, so if it's individual houseplants or puppy dogs or turkeys or, you name it, if they're not human experimental units, that's awesome. That's what we use. However, when it comes to humans, they don't really like being called experimental units, so we call them subjects or participants. The specific values that the experimenter chooses for a factor are called the levels of that factor, and a treatment is a combination of specific levels from all these factors that an experiment unit receives. We are really going to focus on very simple experimental design where the treatments are comprised of just one particular explanatory variable, and so we'll just have different levels of that single factor. Okay, so let's say somebody looked at the results of the study in California that the students in the music group had higher GPAs than the students in the non-music group. And so they want to know, if it is actually the participation in the music program that's causing the increase in GPA. So here's an experiment based on trying to establish that causal relationship. 100 freshman volunteers would be randomly assigned to either being involved in music or not being involved in music, with 50 in the music group and 50 in the non-music group. The grades of the two groups would be recorded throughout high school, and the group's average GPAs compared upon graduation. So our subjects would be the 100 freshmen. The factor is musical involvement. Either they are or they're not. They are assigned to that at random. And then our response variable is going to be the GPA. That's how we're measuring a difference in academic performance. So there are some principles of experimental design that we must employ. One is control. We control sources of variation other than the factors we are testing by making conditions as similar as possible for all treatment groups. So that's why they're taking one group of freshmen. They should be from one high school. Everything that can be made the same should be made the same for all the students other than the critical factor, okay, which level of the explanatory variable they receive. So you want those kids treated the same, except that one group is going to be involved in music and the other group is not. The second is that we need to randomize. Randomization allows us to equalize the effects of unknown or uncontrollable sources of variation. We control what we can directly. If we can't control it or we haven't thought of it, so we can't eliminate it, what we do is we make sure that those forces are acting equally across the treatment levels among all the different groups. So even though this does not eliminate the effects of these forces, it spreads them out across the different groups so we can see past them. Without randomization, you do not have a valid experiment. That's why this is the critical characteristic or principle of experimental design. And you will not be able to use the powerful methods of statistics to draw conclusions from your study. The third principle is replicate. And there's actually two meanings of replicate. The one that we're interested in particular is repeat the experiment, applying the treatments to a number of subjects. The outcome of an experiment on a single subject is an anecdote. It's not data. It's just something interesting that happened once. So we want to have multiple subjects within our experiment. The other meaning of replication is once results are established, if we establish a causal relationship, let's say we did this experiment at Houston Christian, that's great. It's great to know that at a private Christian high school in Houston, being in a music program causes students to have higher grades. But what about in public schools? What about in other states? There's all kinds of other situations that people would like to know if there's a cause and effect relationship. And so being able to replicate the experiment in other settings is beneficial. Okay, so back to what we're actually interested in. When the experimental group is not a representative sample of the population of interest, we might want to replicate an entire experiment for different groups in different situations. So there's that other kind of replication that's also important. Typically, because you're using volunteers, you don't randomly select people to be part of your experiment. You randomly assign them to treatments, but you typically have to have volunteers. This concept of replication is also really important. Okay, so one of the things that makes it easier for people to replicate your experiment or to even understand what you did in your experiment is to use a diagram. So it really emphasizes the random allocation of the subjects to the two groups in the treatments. Here, typically we make a statement about how many subjects. We'll have 100 freshmen are randomly allocated, and then we combine these two into one little statement here. It would be music group, and you would say 100, non-music group 100, and then here we're going to compare, and we put what our response variable is, in this case GPA. So we see a difference in the GPA. Well, couldn't that just happen by chance? Okay, couldn't it just be that in this case one group had a higher GPA versus the other group? Well, we actually have processes for doing this, and this is one of the things that we do in AP Statistics in the second semester. We determine whether or not the differences we're seeing are what are called statistically significant. If they are statistically significant, that means that the difference that we're seeing is not likely to be due to chance alone. Okay, it's not just the luck of the draw that this time this group did better than the other. Both experiments and sample surveys use randomization to get unbiased data. It's important you understand the difference between the two, but because they do so in different ways and for different purposes. Sample surveys try to estimate population parameters. They try to estimate something true about a bigger population. So the sample needs to be as representative of the population as possible, and so they employ random selection from the population. Experiments, on the other hand, try to assess the effects of treatments, and experimental units are not always, in fact, they're seldom drawn randomly from a population. Instead, they're randomly assigned to treatment groups. Okay, so in experiments, we often want to compare a situation involving a special treatment to the status quo situation. Okay, if we're trying to see if something new is more effective than what's being done, if we come up with a new pain medication and we want to know that it does better than acetaminophen, Tylenol, then we would have a control group of people that took Tylenol when they had headaches and a control group of people who took this new medication whenever they had headaches. We might even want to include a third option in a minute that we're going to discuss called a placebo. A baseline business as usual measurement is called a control treatment, and the experimental units to whom it is applied is called the control group. And so another important concept to come in mind is blinding. Experimenters usually are rooting for the new treatment, the new drug, the new program, the idea that music increases GPA. There's usually a side that the person who's designing the experiment is rooting for. So it makes it really hard for them to assess the response, even when they try without bias, even when they're trying really carefully. So in order to avoid the bias, blinding is often used. There are two main classes of individuals who can affect the outcome of the experiment. Those who could influence the results, the subjects, treatment administrators, technicians. We really focus on the subjects here. Because of your own personal bias, you may think that one treatment over the other is going to be more effective. And then those who evaluate the results, the judges, treating physicians, etc. So basically, what that means for research teams is you've got to have some people, especially the evaluator, the person who's going to actually evaluate the response variable, make judgments about that. That person needs to not know what treatment each individual receives, or that could influence how they judge the response. When every individual in either one of these classes is blinded, an experiment is said to be single blind. Okay, you are going to be aware of whether you are participating in a music program or not in a music program. And so there is no way that a subject could be blinded in that situation. However, the teachers who were grading all the classwork for the students could be blinded to that. It'd be a little tricky, but that could happen. So it could happen that it was single blind. Now, in every experiment, there has to be at least one person who knows which treatment each subject is receiving, but that person shouldn't have direct influence, especially on the evaluation process, okay? Or perhaps even, any other aspect other than assigning the treatment. That's that person's job, and then that person's job is to go, okay, these results, these response variable results, correspond to somebody who is in either group. When everyone in both cases is blinded, the experiment is called double blind. And really the case we're concerned with there is that if the subjects don't know and the person doing the evaluation doesn't know, then we have a double blind experiment. Okay, earlier I said there's a certain type of control that if we were testing a new headache pain medication against Tylenol, acetaminophen, we might want another treatment, and that would be a placebo treatment. Often, simply applying any treatment can induce an improvement. Okay, your brain thinks you're going to get better, and so you do. To separate out the effects of the treatment of interest, you can use a control treatment that mimics the treatment itself. A fake treatment that looks just like the treatment being tested is called a placebo. Placebo are the best way to blind subjects from knowing whether they are receiving the treatment or not. So if we were testing new headache medication against Tylenol against the placebo, you would just make sure all three look exactly alike. The subjects would not know which one they were receiving. The person who then later talked to them and asked them about their reduction in headache pain, that person wouldn't know either, but some other person is going to be like the keeper of the data and going to know who received what treatment and then what kind of response they had. The placebo effect occurs when taking the sham treatment results in a change in the response variable. This highlights both the importance of effective blinding and the importance of comparing treatments with a control. Placebo controls are so effective that you should use them whenever you can as an essential tool for blinding. The best experiments are usually randomized, comparative, double-blind, and placebo-controlled. All right, so let's look at an example. A professor wanted to determine if recopying notes helps a student retain more information than simply reading over class notes. She arranged for 200 undergraduate students to participate in the experiment. The subjects were all students in the same large section of a U.S. history class. So there's the control of other variables, okay? They're going to take the class same time of day, same days a week, same professor, so many variables are the same. One group spent 1 hour 3 times a week recopying notes, and the other group spent 1 hour 3 times a week reading over class notes. At the end of 3 weeks, an exam was given, and the average score of the two groups was compared. And so we're going to analyze this experiment. So who are the subjects of this experiment? 200 undergraduate students in one large section of U.S. history. Okay. It's a clear description of who the subjects are and also an indication of how many. What are the treatments? Well, recopying notes and reading over notes for 1 hour 3 times per week. So each one of those volunteers is going to be randomly assigned to one of those two treatments. What is the response variable? What are they going to measure at the end? The score on the exam. Everybody's score on the exam is then going to be averaged according to treatment group membership, and you're going to end up with a recopy average and a read over it average, and you're going to compare the two. Okay, so let's show the experiment in a diagram. All right, so you always want to put how many volunteers you have and a little descriptor. So we've got 200 undergraduates there, and they're going to be randomly assigned to one of two groups. The one group, they're going to recopy notes, and there's 100 of those students. Here we've got 100 students who are going to be reading over notes, and then at the end we're going to compare. That's really important. You have to have the compare there, the average exam score. Guys, don't look for ways to do shortcuts on the diagram. The diagram is the shortcut. Okay, the diagram is the way of conveying what's going on in a way that reduces the amount that you have to write. So here we have who the subjects are and a reassurance that there was random assignment. We've got our levels, our treatments based on our explanatory variable of study method, okay? And then we have the comparison of our response variable. All of those are critical for understanding exactly what's going on in the experiment. Okay, thank you guys. That's it for data creation. Do the problems to try on your own, and I will see you in class. Have a good day.